pure elements which we are using a semiconductor like a silicon and gallium. These silicon and gallium are at room temperature. They are not, or we can say at absolute zero temperature. They are not going to act as a conductor. They are going to act as an insulator. So they are having the covalent bond because all silicon and germanium belongs to this fourth group element. That's why they are forming the covalent bond. And to break the covalent bond, we are supposed to provide the heat, or we are supposed to provide the electrical energy. So due to which what will happen, the material is going to the electrons are going to break the covalent bond, and they will make themselves free from the outermost cell of the atom and placed in the interstitial void positions, because of which they will become the free electrons and they can conduct the electricity. That is what relatively at higher temperature. But we are also having this extrinsic semiconductor. Okay? Because silicon and germanium we cannot use at room temperature. That's why we need something which can conduct electricity at the room temperature. So we are going to mix the impurity with the pure materials like silicon and germanium. With that we are going to mix the impurity. So that will become the extrinsic semiconductor. This extrinsic semiconductor are going to these extrinsic semiconductor are called as your impure material because of the addition of external element or addition of your impurity. So that process is called as your doping process. When we are adding the impurity to a pure material, a pure semiconductor, that process is called as your doping process. And the material which we are add there, that is called as your dopant. Okay, so here in this slide what you can see is that I have drawn two type of extrinsic semiconductors. Okay, that is, one is your p type semiconductor, another one is your n type semiconductor. Okay, so this one is called as your p type semiconductor and this one is called as your n type semiconductor. Why? Because here the charge carrier are the holes, because here the charge carrier are the holes and here the charge carrier are electrons. So what we are doing here is that free electron. So what we are doing is that we are adding the material from third group and from fifth group. So if we will add the material from third group, then what will happen, because its valence or the outermost cell is having only 3 electrons, so it will be make a covalent bond with the 3 neighboring silicon atoms, but one silicon atom will not form any bond with the dopant. So there will be a hole created over here, and this hole will be we are considering is the from the conduction from the valence band, and that is going to be the reason why electricity can be passed through the material. That's why this hole is called as a charge carrier. Similarly, if we go for the n type semiconductor, here we are using a dopant from fifth group element. So in fifth group element, the outermost cell is having how many electrons? 5 electrons. So out of those 5 electrons, 4 electrons are going to make bond with the 4 neighboring silicon atoms, but one will be there which will be free and placed in the interstitial void position, and this is a free electron. And we know that this free electron is able to conduct the electricity, that's why it is a charge carrier. Then we will see what is then we saw what is the temperature dependence of intrinsic semiconductor. Okay, for which I have told you one term is your Fermi energy, right? Fermi energy and Fermi level. So as I told you about this Fermi energy and Fermi level, you are going to read about this again in detail in your high semester. As of now, just remember that this energy and this energy level is that one which is a maximum energy a electron in a material can attain. Okay, if I am considering some x material, for that x material, the electrons can get the maximum energy, that is called as your Fermi energy, at absolute zero. Remember, this is the condition. Okay, if you increase the temperature, no, that energy, maximum energy at energy attaining statement is going to increase. Okay, the maximum energy value is going to increase, but at absolute zero, whatever the maximum energy a electron in a material can attain, that is called as your Fermi energy. And if we are considering various temperatures and we are plotting it as a graph, it will come as a band, that is called as a Fermi level. Okay, so in case of your intrinsic semiconductor, what happens, the number of free electron, if the material possesses some any amount of number of free electron, means in the valence band that many numbers of holes will be present. Okay, so I can say that in intrinsic semiconductor, number of holes are is equal to number of free electrons. Okay, so this number of holes we can see this number of holes in the valence band, but this number of free electrons we see in the conduction band. That means if you are taking a room temperature or absolute zero temperature, at that time there will be no free electron available and there will be no hole is available. Now as I am going to give the external excitement, due to that what happened, the electrons here will break the covalent bond and jump to the conduction band, right? From here valence band to conduction band they are going to jump because of your external excitement. So the number of electron which will jump from valence band to conduction band, that is equal to the number of holes created in the valence band. That's why it will always balance each other. Due to this what happened, this because always it is going to balance each other, that is why this Fermi energy will always lie at the average value of EC and EV. Okay, EC EV means what? The minimum energy level of conduction band is EC and the maximum energy level of valence band is EV. Okay, so the average or the at the mid of this distance between EC and EV, the Fermi energy is going to be lie. Now as you are going to excite more and more, the more electrons are going to be jumping to the conduction band from valence band. The more electrons jump to conduction band, the more hole is going to be created in the valence band. But as much as you heat is also, how much you heat until it burns out, the number of electrons is never going to surpass the value of number of holes. It will always balance each other. That's why whatever you try over here, without adding an impurity, how much temperature you increase, then this energy level or Fermi energy level is not going to change anyway. That's why we can say that here the Fermi energy is temperature independent for intrinsic semiconductor, and the conduction capacity of the semiconductor, intrinsic semiconductor, is going to increase if we increase the temperature. So I can write over here like that. So what I can write here, the Fermi energy of intrinsic semiconductor is temperature independent and conduction capacity will increase with increase in temperature. Okay, this is what is the temperature dependence of semiconductor. Is it fine? Did you have any doubt in this one? If you are having any doubt, you put in the chat box. I will read it and I will clear your doubt. Whenever you are getting doubt, you put the message. Okay, I will read and clear it. So I am continuing with the same topic. If whenever you get doubt, you put the message. Okay. Now we will see this extrinsic semiconductor. Okay. As I told you, extrinsic semiconductor are of two types. So one is your N type, another one is your P type. So in N type semiconductor, what happens? We are adding the 5 valency or fifth group elements. That's why you will be getting over here the free electrons, isn't it? So that is why, because it is giving us free electron, we call it as a electron donor. What we call it is a electron donor. So in N type semiconductor, we find the electron donor. This electron donor is possessing some energy level, that is called as your ED. Okay. Now as it is donating the electron, here the number of free electron is more than the number of hole. So if we consider at absolute zero, this number of holes will be zero only. At absolute zero, the number of holes are always zero. Why? Because when we are doping with a fifth group element, we saw there is 4 bonds are created, right? 4 covalent bonds are created between the fifth group element and the fourth group element, either silicon or germanium. Okay. So as you see this graph in this picture here, as you see here, there is no free holes are present, there is no vacant space is there, all electrons are occupied, all in the outer cell, but there is a free electron is present over here. That's why at absolute zero, the number of holes will be zero only. Okay. As you are going to give the external excitement, the covalent bond will break and it will create some holes and it will create some free electron also. But when you are giving the excitement, at that time the number of holes created will be equal to the number of free electron jump to the conduction band. But before that also, there will be a few number of free electrons present in the conduction band. So always this number of free electron cannot be less than the number of holes or cannot be equal to the number of holes. So always this condition is going to be satisfied always. Okay, for a N type semiconductor. So you can consider this is always, this is going to be satisfied. Okay. So I can say that because the number of free electron is more than the number of holes. That's why the free energy, the Fermi energy of N type semiconductor will lie towards the conduction band because of presence of free electron. Here major charge carrier is your free electron. Here major charge carrier is free electron. So because here major charge carrier is free electron, that's why what happened? The Fermi energy is inclined towards conduction band. That means this Fermi energy level will be present near to conduction band. So which you can see in this graph. In this graph I have represented this EI is nothing but the intrinsic Fermi energy that always lie at the center between the distance of the co-conduction band and valence band. Okay, between these two lines, this between this EC and EV, the EI will lie at the mid of the EC and EV distance. But here there is this electron donor is there, which is going to possess a higher energy level than that of the Fermi energy level of intrinsic semiconductor. The significance of this line you will understand a little bit later. So what happens here? Due to this presence of ED, that's why the Fermi energy of this particular N-type semiconductor will lie towards the conduction band. You see this blue color line what I have represented over here, that sky blue line, that sky blue line is nearer to the conduction band. Now as you will supply the heat over here, more electrons from this valence band is going to jump to the conduction band. So here holes are going to be created. Now the holes created means they are also going to help in conducting the electricity. So they are also the charge carrier. So here the energy level is now, if you increase the heat, the energy level, the Fermi energy level is going to decline towards your valence band because of the holes, number of holes are increasing over there. Now you will say, madam, okay, the number of electrons are also increasing accordingly, no? So yes, number of electrons are also increasing accordingly. If you are increasing the temperature, the holes are created, means electrons are also increasing. But after holes are created, no, the conduction of the electricity is going to be distributed among the holes and the charges. That is why the Fermi energy is going to decline towards the conduction band. But even though it declined towards the conduction band, it will not cross above the intrinsic energy level. Why? Because it is always significant that the number of electron is more. If number of electron is more, that means more amount of power is conducted by the electrons only. That's why the energy will always lie nearer to the conduction band rather than the valence band. Okay, so what will happen over here, as I told you, if some such thing is going to happen, no, at that time what will happen, this, so as I told you, here what will happen, if I am going to increase the temperature, if I am going to increase the temperature, that means number of holes are also going to increase. Number of holes are going to increase, which will represent that the Fermi energy will incline towards valence band. Okay, it will incline towards valence band. Even though it is inclined towards valence band, it is not going to cross the intrinsic Fermi energy level, because number of electron is greater than number of holes. Okay, so now we can see here, if the graph is like that, then what we will observe here, so if I am increasing the temperature, then so if I will increase the temperature, then what will happen, then this EF value, what is represented over here, it is gradually going to decline towards this EI, but not going to cross that line. Okay, that is what is this line represents. Okay, black color line, what you observe here, no, that is what. So if I'm increasing the temperature, the inclination of this energy level is towards EI, but it will never cross this EI value, because number of holes is always more than that of the number of electrons. Sorry, number of electrons is always more than that of the number of holes. Okay, this is what is for your n-type semiconductor. So basically, if we put in n-type semiconductor, the Fermi energy is going to incline towards the conduction band, not crossing the EI value. Also, the conduction of the material is going to increase. So this statement holds good for every type of material. Conducting capacity will increase with increase of temperature, holds good for everyone. Holds good for every type of material, every type of semiconductor. Okay, so what I am saying here is that, so if you increase the temperature, then both semiconductors are going to conduct more electricity. Only thing is that this energy level or Fermi energy is going to be showing different property. Okay, now we will go for this P-type semiconductor. In P-type semiconductor, we are adding in P-type semiconductor, what we are adding? We are adding third group element. Right? As we are adding third group element, we are adding third group element. If we add third group element, so holes are going to be created. So holes are here the major charge carrier. And in this case, at absolute zero, number of free electron is equal to 0. And here number of holes are more than number of free electron always. Okay. So here what happened is it is not donating any electron, it is accepting the electron, right? That is why it is called as your electron acceptor. Okay, it is called as your electron acceptor, and because of which it is also having a energy level of EA. And here the Fermi energy will be lying. Fermi energy is lying towards or lying near, we can say it is lying near the conduction band. Okay, sorry, near the valence band. Okay, so as you can see in this graph here, as you can see, this is the red color one is the valence band, this dark blue color is the conduction band, and this dark blue here is the EI value is the intrinsic energy level, and EA is the accepted energy level. That means the doping what we dopant what we added, for that the electron EA is the energy level, and the Fermi energy is lying between this EA and the valence band, right? So this is called as your EF. Now what happened, as I told you here, if you increase the temperature, then what will happen? More electrons are going to be breaking the covalent bond breaking the covalent bond from the material and jump to the conduction band. So free electron are jumping from valence band to the conduction band. So what will happen? More number of holes are going to be created in the valence band, and more number of electrons are going to be created in the conduction band. So the number of electron as it is increasing, that is why the Fermi energy here is going to increase or incline towards the increase or incline towards the intrinsic semiconductor or intrinsic energy level. Okay, but it will never overcome, or the energy will never go beyond this EI value. Why? Because here how much you try, the number of holes is never going to be equal with the number of electron. Always the number of holes are going to be more only, so they will be the major charge carrier. So the energy is never going to overcome the EI value. So basically, if I want to put this one in a simple term, I can say that here if we increase the temperature, it is going to increase the number of holes. Because of which what will happen? The Fermi energy will start to increase, or will incline towards conduction band, but it will never cross the intrinsic Fermi energy level. Why? Because number of holes are always greater than the number of electrons. Okay, this is what is the, and holes are the major charge carrier, because of which this energy level or the Fermi energy level of an in p-type extrinsic semiconductor is going to increase, but it will go up to ei value only. So this, as I told you, this term is holds good for everyone. The conducting capacity of the material is going to increase if you increase the temperature, but along with that there is a change in the Fermi energy we observe. That is what you observed here in the black line. Okay, in case of n-type semiconductor, if you increase the temperature, the Fermi energy is going to decline towards the ei value, and in p-type semiconductor, if the temperature is increased, the Fermi energy is going to increase towards the ei value. But in both the cases, that is not going to cross the ei or intrinsic and Fermi energy in any way. Okay, is that clear? Do you have any doubt? You can put in the chat box your question. Are you people listening or sleeping? I am getting doubt. If people are not asking any doubt, means what will I get it from it? Okay. Somehow you will read again and you will ask me the doubt. Okay. So now see here, we will go for the next type of next topic of your syllabus. That is your compound semiconductor. So in the type of semiconductor, as I told you, there are two types of semiconductor: intrinsic and extrinsic semiconductor. Similarly, we are also having another type, another classification based on doping only. Okay, it is called as your elemental semiconductor or compound semiconductor. So when I am saying elemental semiconductor, that means these are the elements which are found in your periodic table. Okay, so in periodic table, fourth group elements are there, right? The fourth group elements are like your what I can say is your carbon, silicon, gallium, lead, and lead, all these things. Okay, these are the four I remember. So these are the four different electrons we are the elements we are find in case of your fourth group element. Okay, also we find in fourth group we are finding the tin. Okay, these are nothing but your fourth group elements. Among those fourth group element, As I already told you that if we go from the top to bottom in the periodic table, in fourth group we see that the temperature the conducting capacity is going to increase. So what are the elements in fourth group? As I told you, carbon, one minute. Okay, carbon, silicon, germanium, tin and plumbum, sorry, tin and lead. Okay, these are your fourth group elements, right? So as we know, carbon is an insulator. So if we go downward like this, no, the conducting capacity is increasing. So when I go to this tin and lead, they are the good conductor of electricity. When I go for this carbon, this is an insulator. Okay, this is an insulator except graphite. Okay, so this is conductor, but these two are having semiconducting capacity, right? So these are your elemental semiconductor, because they are the elements. There is nothing we are adding, they are pure elements. Okay, but it is not this silicon and germanium is not cannot be used always, because of their limitations in their property. Okay, because of the limitations in their property. And also in silicon and germanium we cannot tune the energy gap. As I told you, in this case, in the case of your uh, conduction energy band, we see that the conduction band and the valence band are having a gap of energy, right? This eg value cannot be tuned or cannot be controlled in case of your elemental semiconductor. But that is why what we are going is that we are going opting for the compound semiconductor. Now, to get a compound semiconductor, it is not always mandatory that you have to use the silicon and germanium only, or we have to use only the fourth group element. No, we can get this semiconductor with the third group element, second group element, fourth group element as well. Okay, so here in compound semiconductor, what we are doing, we are using two or more than two elements to form a compound which will show the properties of the semiconductor. Now, if I am saying something like that, we are going to mix two or more more elements, means we cannot go for boron nitrides. Okay, we cannot go for boron nitride. Not boron nitride, boron oxide, or let us consider like your aluminum selenide. Okay, the aluminum selenide, if we go for, no, then it will not act as a semiconductor. So to make semiconductor, we are to mix the second group element with the sixth group element. We have to mix, or we have to form a compound between third group element and the fourth group element, or we are supposed to form a compound between fourth group element and fourth group element. Okay, what you observe over here, if I am taking second group element, that means I am taking also the sixth group element. Okay, why? Because we know that if we are supposed to form a covalent bond over here. So to form a covalent bond, there should be sharing of electron. So that is why this is the combination of the elements by which we are going to get the compounds. Now, if I am considering these three type of combination, they are going to give me the binary compound semiconductor. Okay, they are going to give me the binary compound semiconductor. Why? Only two elements are used here. Example, gallium arsenide. Using third group, arsenic is from fifth group. They are from the compound, act as a semiconductor. As they are having only two compounds, many type of binary compounds. Okay, there are many types of gallium arsenide, aluminium arsenide, indium arsenide, then aluminium nitride, gallium nitride, aluminium phosphate, gallium phosphate. Okay, like that we can make many type of binary compound. Now, if I will make the alloy binary compound semiconductor, then I will get ternary compound semiconductor. As you can see, gallium arsenide and aluminum arsenide are used to form this alloy, that is your gallium aluminum arsenide. Okay, so these are your binary compounds. So as I told you, the binary is these are your compounds, okay, or we can say alloy compound. So binary semiconductor we can make between second and fourth group, third and fifth group, and fourth and fourth group. Similarly, ternary or can be formed between the because of the alloy between binary and ternary with 3 elements. See, now I cannot make from gallium arsenide and aluminium phosphate. Okay, that's not ternary one. The ternary means 3 elements to be there, and that should be alloy of 2 binary compound semiconductor. Okay, so this binary and ternary compound semiconductors are in multiple use, are the vast use of this type of elements only we are seeing in our day-to-day life. Okay, there's many and many more people already know. Semiconductor devices, we are surrounded with semiconductor device, each alternate element. Okay, starting from your kitchen gadgets to your household gadget to your industrial application, wherever you see, wherever we are having these digital communication systems, there we are finding out the application of your semiconductor. The vast application of this binary and ternary semiconductor you see in your mobile phones, television sets, laptops, computers. Okay. Otherwise, I will go for the next topic. So as I told you already, remember that this elemental semiconductor are silicon and germanium. But when I go for compound semiconductor, that may have silicon or may not have silicon. If we are having silicon and germanium with the doping elements, then it will be your extrinsic semiconductor. But if we are having other than this silicon and germanium, other semiconductors like gallium arsenide, this is not a extrinsic semiconductor. Remember this one. Intrinsic semiconductor are the silicon and gallium. Extrinsic semiconductor are the silicon based extrinsic semiconductor or gallium based extrinsic semiconductor, where we are adding either third group element or fifth group element. But when it comes to compound semiconductor, there the elements which we are using that might belong to the fourth group, might not belong to the fourth group as well. They might be from third, fifth, or second, fourth, like that. Okay, so don't get confused between the extrinsic semiconductor and the compound semiconductor. Okay, compound semiconductor may or may not be extrinsic semiconductor, but extrinsic semiconductor will always fall under the category of your compound semiconductor. Remember this point. Okay, so here also the temperature is going to play a role. If you increase the temperature, the free electrons are going to, number of free electrons are going to increase, or the number of holes are going to increase, and they will act as a semiconductor. Their conducting capacity is going to increase. Okay, and generally at room temperature, these compound semiconductor are very useful. Clear? We are left with another one topic, that is your amorphous semiconductor and organic semiconductor. Okay, amorphous and organic semiconductor. So amorphous solid and crystalline solid. Do you know the difference between amorphous solid and crystalline solid, right? In case of your crystalline solid, we know that okay. So in case of crystalline solid, we know that it is going to have a characteristical geometrical form. Okay, characteristical geometrical form means what? As I told you, they are possessing a particular crystal structure like FCC, DCC, hexagonal, close packing, like that. Okay, so they are having a characteristical geometrical shape, or we can say definite geometrical shape. Okay, and that definite geometrical shape is going to represent or going to repeat, or that what wherever you go inside the solid, no, you will see this definite crystals or definite geometrical structure repeating itself. Okay, geometrical structure, but amorphous solid is not having this definite geometrical structure. There, in this case, you don't see any long range definite structure. Okay, like your crystalline solid. Here, whatever the structure you will see, that is very short range. Means in a few area the geometrical shape is definite. Another few area the geometrical shape will not repeat itself. Right, like that. Okay, that is what is the difference between a crystalline solid and a amorphous solid. That is a basic definition wise, this is a difference. Okay, so what happened, because these materials having this definite structure, that's why they are having a sharp melting temperature. Sharp melting temperature means what? Like they will not give us a intermediate state. Okay, if you heat it, then directly they are going to melt down. Okay, at a particular temperature they will start to melt down, but your amorphous solid is having a range of temperature where you get this gummy like this intermediate state between the solid and the liquid. Okay, so I can say here that it is also having a sharp melting temperature. Okay, this thing what I am telling here is that no, these are holds good for semiconductor as well. Okay, because semiconductor are also solid, they are also possessing the similar properties, same properties like your amorphous solid and crystalline solid. Okay, those are like, if I am considering silicon itself, then there is a compound from for silicon which is crystalline in nature, but another compound from silicon is there, that is amorphous in structure, or okay, amorphous solid. So they are both are possessing different properties, but they both are the semiconductors. Okay, that's why I am telling you this difference. Also, what happens when you go for breaking a crystalline solid, no, so there are cleavage points. Cleavage point means there are certain points are there, if you break that one, no, at that plane only these crystalline solids are going to be break down. But in case of amorphous solid, that particular cleavage plane is not available. So I can say in crystalline solid, cleavage plane is there. Cleavage plane means what? There, if you want to break the crystalline solid, no, that is the particular. There are some particular planes are there on which they are going to break down. But your amorphous solid is not having such any such plane. So if you break it, randomly it is going to start to break down. Just as you see in case of your glass, if you want to break the glass, there is definite planes are there through which that cracks are going to propagate and they will break down. But in amorphous solid, that type of particular property is not available. Also, this amorphous solid, this crystalline solid are anisotropic in nature. Anisotropic means what? Anisotropic means they are going to show the directional properties. That means if you change the direction of the plane, or like we have read the uh, crystallographic plane. Okay, so I can say in one direction a plane is showing some property, in another direction what is your directional property. Like I told you, as I told you, in a duster, one plane might be a good conductor of electricity, but another plane is not conducting the electricity. That is what is a direction. When you are changing the direction, the properties are also changing. But in case of your amorphous solid, that anisotropic nature is not available. It is a isotropic material. Okay, so amorphous solid are very less rigid, but these crystalline solid are very rigid by nature. Rigid means very brittle in nature. Okay, so the example of amorphous solids are like Teflon and polyvinyl chloride, polyurethane. These are your amorphous solid. So polyvinyl chloride means PVC. In short term, we are saying PVC. So you are saying no PVC pipes, right? That plastic pipes which we are using, that is polyvinyl chloride. They are amorphous solid. They are made up of amorphous solid. But at the same time, if I see copper and potassium nitrate and glass, these are all the crystalline solids. Okay, this is the difference between the amorphous and crystalline solid. The same difference will holds good for amorphous and crystalline semiconductors. Okay, so in next class we are going to go about amorphous solid, and then we will organic semiconductors, and we will wind up the semiconductor chapter over there. Okay, in the meantime, if you are finding any doubt in this case, you can ask me in your chat box or in personal WhatsApp. Okay, so today I am ending the class over. Someone is raising hand. Okay, Labanya, you are able to unmute yourself. If you have any doubt, you can ask your doubt. And Raj also.
Ma'am, yesterday's and today's class, please share. I have a signal problem.
What you want to say? What you want? Your voice is not audible. You want video?
Yes, ma'am. Yesterday's record and today's record.